My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about the atomic structure. We'll learn about Bohr's atom. Also, we'll go a little bit further to study the device used to analyze light. Then we'll be able to get an idea about the different types of the spectra of the atom. So let's get started. Atomic spectra and Bohr's model. Bohr's atom, what about it? At the center of the atom, there is a positively charged nucleus. Once again, at the center of the atom, there is a positively charged nucleus. Negatively charged electrons, so electrons are negatively charged, but the nucleus is positively charged. Negatively charged electrons revolve around the nucleus in orbits in energy levels. Each orbit has a definite energy value. Electrons revolving around the nucleus can only occupy certain set of allowable orbits. Let me say it again. Electrons revolving around the nucleus can only occupy certain set of allowable orbits. The atom is electrically neutral. The question is why? Simply because the number of electrons are negatively charged, number of electrons around the nucleus, which is positively charged, equals the number of positive charges in the nucleus. So once again, the atom is electrically neutral since the number of electrons around the nucleus equals the number of positive charges in the nucleus. An electron does not radiate when it is in one of the allowed orbits. And this statement was contrary to Maxwell's theory, but Bohr actually evaded the conflict with this theory. But how? By just stating, yes, something. By stating that Maxwell's theory did not apply to systems of atomic size. Thus, he postulated that an electron could revolve in any of the permitted orbits indefinitely without radiating energy. To radiate, so now we are talking about the situation in which the atom emits light. To radiate a photon, an electron should make transition from higher energy level E2, so E2 denotes, yes, higher energy level. Electrons should make, yes, transition from higher energy level to lower energy level. Okay. In this case, a discrete amount of energy is released in the form of a photon. Energy of the photon is given from the expression h nu, and of course h is Planck's constant, and this discrete amount, yes, is equal to the differences between the two energy levels, E2 minus E1, okay? Nu is the frequency of the emitted photon, and as I said, h is Planck's constant. the electric forces, we call it Coulomb forces, and mechanical forces, Newton's forces, are at work in the atom. Electric and mechanical forces, yes, work at atom. They are applicable, yes, on atoms. And here we've got something very important. We can estimate the radius of the orbit, okay, orbit of the electron, by taking into consideration that the wave accompanying the motion of an electron should form a standing wave. Okay, should form what? A standing wave. A standing wave is only formed when the circumference of the orbit is equal to a whole number multiple of the wavelength. A standing wave is only formed when the circumference of the orbit is equal to a whole number multiple of the wavelength. So circumference, which is 2 pi r, should be equal to whole numbers of wavelengths in lambda, and could be 1 or 2 or 3. Circumference of the innermost orbit is equal to 1 wavelength of the electron wave. The second orbit has a circumference of 2 wavelengths. Third orbit has a circumference of 3 wavelengths, and so on. And now talking about line spectrum of hydrogen. Line spectrum of hydrogen. When hydrogen atoms are given energy, they absorb different amount of energies. They then make transitions to higher energy levels. Electrons remain in the excited levels for a short period of time called lifetime. It is about 10 to the power of negative 8 seconds. Then they fall to their ground state. Okay? When an electron makes a transition from a higher energy level denoted by E2 to a lower energy level denoted by E1, what happens? Yes, a photon is emitted. It emits a photon having energy equal to the difference between E2 and E1. So E2 minus E1 equals h nu. The ground state has the lowest energy. Since electrons in different hydrogen atoms absorb different amounts of energy, they radiate different amounts of energy. The emitted photons will have different frequencies. The color of the light seen is a composite of all the different frequencies. And now talking about atomic spectra. Series for hydrogen atoms. So in front of you, we've got, yes, a diagram that shows energy levels of an atom, hydrogen atom. Okay, when the excited electrons falls from higher energy levels to the energy level, the innermost energy level denoted by n, which is equal to 1, what happens? We've got a series. We call it Lyman series, and it is in the ultraviolet series. And what about if they fall to, if they relax to the second energy, okay, N2, Balmer series is produced. And when they relax to N3, we've got Paschens, which falls in infrared region. And we've got bracket series when it falls to N, which is equal to 4. And found when it relaxes to the energy level N, which is equal to 5. We'll take it one by one. First of all, Lyman series. Okay, they are produced when electrons move from higher energy levels to level K, denoted by N equal to 1. This series lies in the ultraviolet region. They've got very short wavelengths. Okay, short wavelengths means high frequencies. And what about Balmer's series? Okay, Balmer's series is produced when electrons move from higher energy levels to level L, where N is equal to 2. This series lies in the visible region. And what about Paschen? Electrons, okay, to produce this series, electrons should move from higher energy level to level M, where N is equal to 3. And it lies in the infrared region. Bracket series is produced when electrons move from higher energy levels to energy level N, where small n is equal to 4. And also it lies in the infrared region. And finally, we've got Fund, in which electrons move from higher energy level to level O, where N is equal to 5, and this series lies in the far infrared region. It has the longest wavelengths. And now talking about the structure of the device used to analyze light coming from the atom. Okay, it analyzes light into visible and invisible components. It is the spectrometer. Okay, so once again, it is an optical instrument which is mainly used to study the light emerging from different sources. It analyzes light into its visible and invisible components. It analyzes light into its visible and invisible components. Structure of the spectrometer, structure of the device. Okay, first component, we've got three major components. The first is the collimator. Then we've got a prism set in position of minimum deviation. And the third component is the telescope. Okay, so it is composed of three major components: collimator, prism, and telescope. And how does it work? What about its mode of work? Okay, it is shown in front of you, and we'll mention this in details. So once again, it consists of collimator, and we want to know the function of the collimator. Yes, it is to produce parallel light rays. So the collimator consists of a tube with a rectangular slit of variable width at one end and a converging lens at the other. Okay, so the slit is located at the focus of the lens. So when light passes through this slit, yes, it emerges from the lens in form of parallel light rays. Once again, collimator consists of a tube with a rectangular slit of variable width at one end and converging lens at the other. The slit is located at the principal focus of the lens, so that the light rays which emerge from the lens are parallel. So the function of the collimator is to produce parallel light rays. Your attention, please. The function, once again, of the collimator is to produce parallel light rays. Second component, as I said, we've got a turntable in which a prism is placed. Okay. The prism is set in the position of minimum deviation. So the prism disperses the light. In this way, light is analyzed. Once again, the prism is set in the position of minimum deviation. So the prism disperses the light falling on it. Disperses light and separating it into whatever colors are contained in the original beam of light. Third component, it is, what about it? It is a telescope adjusted so that the parallel rays entering it are brought to a focus near the eyepiece. How does it work? So right now we'll talk about the mode of work of the spectrometer. How does it work? This is very important. Okay, the light from the source. Light from what? From the source. Okay, is focused on the slit of the collimator by a lens denoted by capital L. Okay. The slit is placed at the focus of the lens L1. So light ray produced by L1 are parallel light rays. Once again, the slit is placed at the focus of L1. The parallel light rays emerging from the collimator falls on a prism which is set in position of minimum deviation, so it disperses light into its components. The telescope is directed to receive light emerging from the prism. Okay, the objective lens L2 of the telescope focuses the rays of the same color. Okay, so once again we'll take it, yes, step by step. Light from the source is focused on the slit of the collimator by a lens, yes, denoted by capital L. The slit is situated at the focus of the lens L1. Okay, the parallel light rays emerging from the collimator falls on the prism, which is set in position of minimum deviation. So the prism disperses light into its components, and function of the telescope, yes, it is directed to receive the light emerging from the prism. Objective lens of the telescope focuses the rays of the same color. And now we've got something important to mention, important hints. When the spectrometers are made for special purposes, they are called spectroscopes. So spectroscope is an instrument for viewing a spectrum. In the previous instrument, if the light dispersed by the prism is directed to fall on a photographic plate, the instrument is called a spectrograph. So a spectrograph is a device for photographing a spectrum. Now we'll talk about the conditions fulfilled in the device so as to obtain pure spectrum. Okay? First of all, we should have parallel light rays. This is one condition. And second condition, these rays should fall on a prism set in the position of minimum deviation. And third, we should, have a lens to focus, light rays of the same color. Okay, we'll take them one by one. The usual method for obtaining a pure spectrum is by using, using what? A collimator, in which there is a slit located at the principal focus of a lens to produce parallel light rays on a prism set in position of minimum deviation. This is the first condition. And what about the second? But first, let me say it. We've got a narrow slit at the principal focus of a converging lens to produce parallel light rays. Then we should have a prism set in the position of minimum deviation. Okay, prism disperses light and colors appear. Still we need something. We need a lens, to focus colors, to focus lights of the same color. We need a converging lens to focus the rays emerging from the prism of the same color. Now, what are the conditions necessary for obtaining pure spectrum in the spectroscope? Yes, the slit of the collimator should be narrow and placed at the principal focus of the converging lens of the collimator to produce parallel light rays. The parallel rays emerging from the collimator should fall on a prism set in the position of minimum deviation. Okay, the prism disperses light into visible spectrum, then light, dispersed by the prism is directed to fall on a convex lens, a converging lens to focus the rays of the same color. Okay, we've got questions. Give reason for. The slit of the collimator should be narrow so as to obtain pure spectrum from the spectrometer. Why it should be so narrow? It is a crucial condition to obtain pure spectrum. Okay. The answer is a wide slit is equivalent to, it can be considered as a number of parallel slits. And since each such parallel slit produces its own spectrum, the result is overlapping of colors. Second, give reason. In the spectrometer, the rays incident on the prism should be parallel. Let me say it again. In the spectrometer, the rays incident on the prism should be parallel. If the incident rays are not parallel, this is the answer. The different rays of the same color would deviate by different amounts, and this would cause overlapping of colors. Another give reason. In the spectrometer, the prism should be set in the position of minimum deviation to obtain pure spectrum. Why such position? The position called minimum deviation. In the minimum deviation position, the rays of the same color passing through the prism will emerge out from the prism in the form of a beam of parallel rays. That's to say, in the minimum deviation, in the position of minimum deviation, okay, the different rays of the same color falling on the prism are deviated by the same amount. Hence, all rays of the same color get focused at the same place by the converging lens of the telescope. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.